Okay, so here's a problem. We want to find the absolute maximum moment in this beam. It's 30 feet long. Our vehicle, or our horse cart, or whatever it is moving from the right side to the left side. And I know it's hard to see, but that's an 8-foot difference between the two. So remember in our discussion previously, we need to first find the resultant force and where it would be located here. So I think the resultant force calculation is not too hard. The resultant force will just be 1,200 pounds plus 400 pounds, which I think by my calculation is 1,600 pounds. You may check that. Is that okay? So where would it be located? Well, this is what I like to do. I like to kind of make a sketch. So there's my 1,200 pound force. And then 8 feet back is the 400 pound force. I guess this cart's being backed across the bridge. And now here in the middle, somewhere, is my resultant force of 1,600 pounds. And let's just say that it's located some distance x from the front. Okay? Everybody see that? So now if I look at this point right here, I'll call it point O. The sum of the moments about point O for the entire load system needs to be equivalent to the resultant system. It's not equal to 0. They just need to be equal. So first I will sum moments at O. And when I do that for the real system, what do I get? I get 400 times 8. So I'll have 400 pounds times 8 feet, which I believe is 3,200, right? And that will be pound-feet. Also, if I sum moments, but this time about the same point, but I only consider the equivalent, what do I get? I get 1,600 pounds. And what's its moment arm? X. Well, these need to be equal. So set them equal. What's X going to be equal to then? 2 feet. So now I have a 1,600 pound force that would be 2 feet from the 1,200 pound force, and that would create equivalent force and equivalent moment. So anytime I can use just the equivalent force to find any kind of reactions or whatever, you should do that. Now what I'm going to have to do first, remember, is I'm going to come over here to the center line of the structure, which would be 15 feet and 15 feet. And I'm going to, for case 1, I'm going to balance the first load, the 1,200 pound, and the resultant load, the 1,600 pound, to be equidistant about the center line. So what would be the distance? I would just take this distance x and divide it by 2. So let's see what that position would be. So here's case 1.
Okay.
Yeah.
Where you going? Can you explain real quick again how you got x and 2?
Oh, well, these two things have to be equal. So I know that from the real loads, the moment about O has to be 3,200 pound-feet. And since I don't know x, about the same point O, the equivalent system is 1,600x. And since they have to be equal, x has got to be 2. Right? 16x equal to 3,200, x would equal to 2. So this would be the same if I had 2 forces, 3 forces, 4 forces, really as many forces as I want. I pick one, and I would get the moment for all the forces about a point, and then I would balance that to the resultant force at one position x. So really, instead of modeling it as a 1,200 pound force going back 8 feet to a 400 pound force, an equivalent model would be a single 1,600 pound force moving 2 feet behind the front. it would create the same moment and the same reactions. So what I like to do is draw the structure, identify the center line. So my first force is here, and that's the 1,200 pound force. And that's 1 foot. And then 1 foot back is the location of my concentrated equivalent, or my resultant force, which is 1,600 pounds. And then how many feet back to the 400? 6. Yeah, if this is 2 feet, then this would have to be 6 feet. So I go 6 feet back, and there's the location of my 400 pound force. So since this is 15 feet and this is 1 foot, that means this is 14 feet. And from the center line, this is 7. 7 from that, that means this is 8 feet. So now I know where every force is. And then, of course, I would still need to possibly look at my reaction at Y and my reaction at B. So there's I've now taken a moving load problem and reduced it to a problem that you've worked many, many times before. Here's some loads. Tell me what the moment is under the first force, right there. So I'm going to cut the structure there, right? So now I'm going to cut the structure. You want to work the left side or the right side? I think the left side is the way to go. So if I'm going to do the left side, yeah. You always cut it underneath the force that you're balancing with the resultant. So since I'm balancing the first force, split the difference, equidistant to the resultant, then that's the place I'm looking for. So this would be from A, that would be 14 feet over. So I know the position, we just have to find the moment. So my free body diagram for this structure looks like this. I just need to find my reaction at A, and then I'll have the internal moment that I'm looking for. So before I even find this reaction, I can see that the moment's just going to be that reaction times 14 feet. So I just need to find AY. So how do I find AY here? Yeah, we'll take the moment about B. Now here's where it gets fun. When you take the moment about B, I don't have to deal with all the forces. I just deal with the resultant. Not the resultant and all the forces. It's either the original forces, this is bold, underline, italics, blinking in red, or the resultant. Not both. So my advice to you is resultant. It's the least amount of work. So I'll come back now and sum moments about B. Make sure it's in equilibrium. Using only the resultant force, the distance from B to the resultant is 14 feet, and it creates positive moments. So I have 1,600 pounds times 14 feet, and the other force in the system is AY, which creates negative moment and has a moment arm of 30 feet. So what's AY equal to?
746.67.
Say that again.
746.67.
746.67. And that's in pounds. Anybody else get that?
Yes.
Cool. So then what do I do here? I sum moments about the cut. And set that equal to 0. And what do I have? Well, I have a positive moment, thing I'm looking for. And then I have AY now, which I've just solved for. I forgot to label it, sorry. Of course, we now know it's 746.67. And that creates a negative moment, so 746.67 pounds. And what's the moment arm? 14. And what's that equal to? close to 10,000 something. 10,000 what? 10,453. That's close enough. 10.43, and that'll be kip feet. So I now know that at 14 feet from A, I have a 10.45 kip foot moment. Is that the highest one? Maybe. We have one more case to check. So let's go to case 2. Since we have 2 forces in our system, we have 2 cases. So again, I'll redraw the system about the center line. Now I'm going to balance the resultant force with the second force. What's the distance between those? 6. So I split that, it'll be 3. So that means 3 feet to the right of the center line is the 400-pound force. 3 feet to the left of the center line is the 1,600-pound resultant force. And then 2 feet in front of that, sorry I didn't leave myself much room there, is the 1,200-pound force. And now we have different reactions at B and A. So I've constructed another statics problem for you to solve, except where am I going to look for this point? Under the 400 pounds. So I'm going to look at, okay, here's my cut, left or right? Right. Hey, look, we went right, we went left. Hey, covered all the bases. So now if you look at the free body diagram for that, using the right-hand side, then now I have an internal moment, a positive moment. Oh, by the way, what would that distance be? If this total is 15 and this is 3, makes this 12. So now looking at a 12-foot section, and it looks like I need what reaction? By. How do I get By? Correct. So let's go back to our free body diagram and some moments about A. Now, when I'm summing moments about A to find By, do I use the resultant force and all the other forces? Do I use all the forces? No. Negative. I use which? Either the resultant force or everything else, not and. Or. Say it with me. Or. How many of you will forget to do that on the exam? More than you think. So remember, or I guess you can choose not to do this problem if you'd like to. Everything's optional, right? So about A, using just the reaction force, what's the distance from A to the reaction force? I left off some dimensions here. So I know this is 15 minus 5. This should be 10 feet, right? So distance from A to there is 12. And that creates negative moment. So I have 1,600 pounds times 12 feet. So that's the moment about A due to just the resultant force. And then I have By, which is creating positive moment, and its moment arm is 30. So what's By equal to? Exactly? 640 pounds. And now that I know By, I can come down here and sum moments at the cut that we made, make sure it's in equilibrium. Looking at this free body, my moment is negative. By creates positive moment times a moment arm of 12 feet. So 640 times 12, the moment is equal to 7,000. So that would be 7.68 kip feet. Which one is bigger? So the maximum moment in this structure is 10.45 kip feet, and it occurs at this position, which is 14 feet from A. So not only do I know the value, I know its location. And now I can design my structure. If this is the only load that's applying to my structure, I can now design a beam section to withstand at least 4.5 kip feet of moment. So any questions about that one? We can work some more if you like. All right, I'll stop that.